The night sky holds secrets that challenge everything we know. Carl Sagan once said that somewhere, something incredible is waiting to be known, and that pursuit defines our journey into 30 intriguing cosmic conundrums explored through rigorous science. This voyage will fundamentally alter how you see our place in the cosmos, revealing why these puzzles matter for our origins and our future among the stars. We will traverse the ghostly pull of dark matter and the crushing depths of black holes, uncovering how science turns baffling phenomena into testable truths. What if the universe is an unfinished symphony and we are only just beginning to hear the notes? How much of reality is truly hidden from our view? By the end, you will grasp the profound connections between the largest cosmic structures and the smallest quantum particles. What part of this cosmic mystery most captures your own curiosity? Our universe is held together by a ghost. For nearly a century, astronomers have known that something invisible, something we cannot see or touch, exerts a profound gravitational pull on everything from spinning galaxies to the largest structures in the cosmos. This is the first great cosmic conundrum, the elusive nature of dark matter. Think of it as the ultimate detective story, where the culprit leaves no direct trace, yet its fingerprints are absolutely everywhere. We see its handiwork in the way galaxies rotate so fast they should tear themselves apart, but something holds them together. We sense its presence in the way light bends around massive objects, a phenomenon called gravitational lensing, revealing far more mass than our telescopes can account for. The pioneering astronomer Vera Rubin meticulously charted these strange galaxy rotation curves, proving that stars on the outer edges moved just as quickly as those near the center. This was a direct challenge to our existing laws of gravity, screaming that a vast amount of unseen matter must be lurking in the shadows, a cosmic scaffold shaping everything we see. So what is this mysterious substance? We know it makes up roughly 27% of the universe's total mass and energy, but it does not emit, absorb, or reflect any light. It is fundamentally different from anything we have ever known. Scientists have proposed several theoretical particles as candidates. One leading idea involves WIMP, or weakly interacting massive particles. These are hypothetical heavy particles that barely interact with normal matter, streaming through you and everything around you by the billions every second without a whisper. Another candidate is the Action, an incredibly light particle that could be flooding the cosmos. To catch these phantoms, we have built extraordinary traps. Deep underground, in mines shielded from cosmic rays, sensitive detectors wait for the once-in-a-lifetime bump of a dark matter particle. Meanwhile, machines like the Large Hadron Collider smash particles together at near light speed, hoping to create dark matter in the debris. Perhaps the most stunning evidence comes from cosmic crashes like the Bullet Cluster. This is a system of two colliding galaxy clusters. Observations show that the visible matter, the hot gas that glows in X-rays, was slowed down by the collision like two clouds of smoke mingling. But the dark matter, mapped through its gravitational lensing effect, sailed right through the crash unaffected. It literally became separated from the normal stuff, proving it is not just an error in our equations, but a real physical substance. This has led some to wonder if we are chasing the wrong ghost entirely. Could our understanding of gravity itself be incomplete? A theory called modified Newtonian dynamics, or MUND, suggests that on very large scales, gravity behaves differently and no dark matter is needed. Yet for most scientists, the evidence for dark matter's tangible presence remains overwhelming. What if dark matter interacts in ways we have not yet dreamed of? Its discovery would not just fill a blank in our cosmic inventory, it would rip open the textbook of physics and force us to write entirely new chapters. It is the hidden architecture of reality, the silent partner to all the stars and galaxies we hold so dear. And as we ponder this immense, invisible presence holding the cosmos together, we are led to an even more profound and unsettling question. What is the mysterious force that is tearing it all apart? That silent partner, dark matter, desperately holds the cosmos together, but a far more dominant and mysterious force is actively ripping it apart. This is the second great cosmic conundrum, dark energy. For most of the 20th century, scientists believed the universe's expansion, born from the Big Bang, was gradually slowing down due to the relentless pull of gravity. It was a logical assumption that everything would eventually coast to a halt or even collapse back on itself. Then, in the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter, made a discovery so shocking it earned them the Nobel Prize. By observing distant stellar explosions known as Type I, a supernova, which act as perfect standard candles because they always explode with the same intrinsic brightness, they could measure cosmic distances with incredible precision. They expected to see these faraway beacons looking brighter than they should if the universe's expansion was slowing. Instead, they looked dimmer. The only possible explanation was that the universe is not just expanding, it is accelerating. The galaxies are flying away from each other faster and faster over time, propelled by some unknown repulsive force. This force is what we call dark energy, and it makes up a staggering 68% of everything in the cosmos. To understand this, we can turn to an idea Einstein himself once proposed and then discarded. He called it the cosmological constant, a sort of inherent energy woven into the very fabric of empty space. This energy has a negative pressure, and on cosmic scales, that negative pressure causes a gravitational push, forcing space itself to stretch. Think of the universe as that inflating balloon, but instead of someone blowing into it, the rubber of the balloon itself possesses a strange, innate property that makes it expand faster and faster all on its own. This is the leading theory for dark energy, the cosmological constant. Yet, this explanation opens up an even deeper problem, the cosmological constant problem. When physicists try to calculate how much energy this vacuum of space should contain using our best theories of quantum mechanics, the number they get is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the entire history of science. This staggering mismatch suggests we are missing something profound, that either dark energy is not a constant at all but an evolving field, or that our understanding of gravity and quantum physics is fundamentally incomplete. The implications of this accelerating expansion are as grand as they are chilling. It dictates the ultimate fate of everything. If dark energy remains constant, the universe will expand forever, leading to a slow and cold big freeze. Galaxies will become so isolated that their light will no longer reach each other, and the cosmic sky will fade to black. But if dark energy strengthens over time, it could lead to a far more violent end, the Big Rip. In this scenario, the repulsive force would eventually overcome all other forces, first tearing apart galaxy clusters, then galaxies, then stars and planets, and finally ripping apart atoms themselves at the very end of time. Is dark energy a fundamental property of the vacuum, a steady background hum of reality, or is it a dynamic field that could change, offering different futures for the cosmos? This mysterious pressure, this anti-gravity that defines our universe's destiny, forces us to look back to the very beginning, to the moment when all of this, the dark and the light, first burst into existence. That mysterious pressure, dark energy, dictates our cosmic future, but to understand it we must return to the very start, to the third great conundrum, the initial conditions of the Big Bang. The story of our universe begins with a singularity, a point of infinite density and temperature where the familiar laws of physics simply break down. This is not merely an explosion in space, but the violent birth of space and time themselves. The very question of what happened before the Big Bang might be a trick of language, as Stephen Hawking suggested, because without the Big Bang there was no before. Time, as we understand it, began at that moment. Yet this profound idea immediately confronts a practical puzzle, the horizon problem. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see a universe that is remarkably uniform. The temperature is the same in every direction we look, to within 1 part in 100,000. But according to the standard Big Bang model, the universe simply did not have enough time for these vastly separated regions to exchange heat and even out their temperature. They were never in contact. How, then, did they reach the same state? The answer, proposed by physicist Alan Guth, is cosmic inflation. This theory suggests that in the first fraction of a second, the universe underwent a breathtaking, exponential expansion, inflating from smaller than a proton to a vast volume in an unimaginably short time. This process would have stretched space itself, smoothing out any wrinkles and creating the uniform cosmos we observe. It also solves the flatness problem. The universe appears geometrically flat, meaning its initial density was fine-tuned to an astonishing degree. Inflation naturally explains this, as the rapid expansion would have flattened the cosmos in the same way blowing up a balloon makes its surface appear flatter and flatter. Our most detailed evidence for this early epoch comes from the Planck satellite, which mapped the cosmic microwave background with exquisite precision. It revealed tiny temperature fluctuations, the seeds from which all galaxies, stars, and planets would eventually grow. These anisotropies are a fossil imprint of the quantum fluctuations that were stretched to cosmic size during inflation. But what drove this inflationary burst and what ended it? The leading ideas point to a hypothetical field, the inflaton field, whose energy drove the rapid expansion. This brings us to the edge of known physics, where we must grapple with quantum gravity, an attempt to unify Einstein's general relativity with the strange rules of the quantum world. String theory, for instance, suggests that the fundamental constituents of reality are not particles but tiny, vibrating strings, and that our universe may be one of many in a vast multiverse. Could it be that our Big Bang was not a unique beginning, but one event in an eternal cycle of cosmic birth? The initial conditions of our universe seem so perfectly calibrated for the emergence of life that it begs for an explanation. Unraveling this ultimate origin story leads us directly to another profound imbalance woven into the fabric of reality, the puzzle of why anything exists at all. For in the first moments of the cosmos, matter and antimatter should have been created in equal amounts, annihilating each other completely and leaving behind a universe of pure light. Yet here we are. That profound imbalance is written into our very existence. One of the greatest unsolved puzzles in physics is why the universe is made of anything at all. In the first fiery moments after the Big Bang, energy should have condensed into perfectly equal amounts of matter and antimatter. For every particle of matter created, a mirror particle of antimatter should have been born alongside it. When a matter particle meets its antimatter twin, they annihilate each other in a flash of pure energy. The entire cosmos should have been a brief, brilliant flash, a return to nothingness. Yet, against all odds, 1 in every billion matter particles survived. everything we see, from the most distant galaxy to the air we breathe, is built from that 1 in a billion residue. This is the matter-antimatter asymmetry problem, and it demands an explanation. How did this perfect symmetry break? The answer lies in a set of conditions proposed by the physicist Andrei Sakharov. First, there must be a process that treats matter and antimatter differently, violating what physicists call charge parity symmetry. Second, the universe must have been in a state of thermodynamic imbalance, out of equilibrium, to allow this tiny preference to take hold and not be immediately wiped out. And third, these interactions must have occurred at a time when protons could be created and destroyed. Scientists call this suite of requirements baryogenesis. We have actually observed a piece of the first condition in action. In enormous particle accelerators like the one at CERN, we can see a phenomenon known as CP violation. Certain exotic particles like B mesons and their antimatter counterparts do not decay in exactly the same way or at the same rate. This is a tiny crack in the mirror of nature, a slight but measurable preference for matter over antimatter. The problem is, the amount of CP violation we have measured so far is far too small to account for the overwhelming dominance of matter we see in the cosmos. It is like finding a single dropped coin when you need to explain a vast fortune. So where is the rest of the effect coming from? The search is on. Perhaps the answer involves neutrinos, those ghostly particles that stream through the universe almost unnoticed. If neutrinos are their own antiparticles, a special class known as Majorana particles, they could have triggered a process called leptogenesis in the early universe. This scenario suggests that an asymmetry in neutrinos could have been transferred into the matter asymmetry we see today. Other theories point to dramatic phase transitions in the primordial cosmos, moments when the fundamental forces of nature split from a unified whole, creating bubbles in the fabric of spacetime where the rules were temporarily different. Within these bubbles, Sakharov's conditions could have been met on a grand scale. We look for evidence everywhere. We study cosmic rays, the high-energy particles raining down from space, and find that antimatter is incredibly rare, confirming the cosmic imbalance. In laboratories, we painstakingly create and trap atoms of antihydrogen, holding them for minutes at a time to see if they behave any differently from normal hydrogen. So far, they seem to be perfect mirrors. What if the universe is not entirely lopsided? Could there be vast, hidden domains of antimatter galaxies somewhere in the void, separated from us by unimaginable distances? Most evidence suggests not, as the border between a matter region and an antimatter region would glow with the intense radiation of constant annihilation, a light we do not see. This fundamental imbalance is not just a historical curiosity, it is the reason we are here. Without it, no atoms, no stars, no planets, and no life would have ever formed. The quest to understand it forces us to probe the deepest laws of particle physics, pushing toward a unified theory of all forces. And as we ponder the delicate conditions that allowed our material world to exist, we are drawn to another, even more elusive shadow in the cosmic inventory, a substance so strange it seems to defy the very laws of physics. The same fundamental imbalance that allowed our existence points toward a deeper, underlying unity. Throughout the cosmos, every interaction, from the orbit of a planet to the fusion within a star, is governed by just 4 fundamental forces. Yet these forces are a fractured family, described by 2 very different sets of rules. The dream of weaving them into a single, elegant framework is perhaps the ultimate goal of physics, a quest known as the search for a theory of everything. Albert Einstein spent the last 30 years of his life chasing this unified theory, convinced that the universe could not be so schizophrenic, that gravity and electromagnetism must be 2 faces of a single coin. He ultimately failed, and the problem has only grown more complex. We now know of two additional forces operating within the atomic nucleus: the strong nuclear force that binds protons and neutrons together, and the weak nuclear force responsible for radioactive decay. Unifying these four, gravity, electromagnetism, the strong, and the weak, into one coherent description is the fifth great cosmic conundrum. Why is this so difficult? Primary obstacle is gravity. The other three forces are described by the quantum framework, a world of probabilities and discrete particles. Gravity, as explained by Einstein's general relativity, is a smooth, geometric warping of spacetime. Getting these two incompatible languages to speak to one another has proven to be the greatest theoretical challenge of the last century. There is a tantalizing clue, however. As we look back in time to the universe's first moments, energy and temperature soared. Under these extreme conditions, the forces we see as separate today begin to merge. We have already successfully unified electromagnetism and the weak nuclear force into a single electroweak force, a prediction spectacularly confirmed by particle accelerators. Theories suggest that at even higher energies, like those just after the Big Bang, the strong force would also join this union, but gravity remains the stubborn holdout. To bring gravity into the quantum fold, physicists have proposed breathtaking ideas. String theory suggests that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrations of these strings would manifest as different particles and forces, with one particular vibration corresponding to the graviton, the hypothetical quantum carrier of gravity. For the math of string theory to work, it requires more than the three spatial dimensions we experience. It demands extra dimensions, perhaps 6 or 7 of them, curled up into a space so small we cannot perceive them. Imagine an ant walking along a vast, tightrope-thin cable. From a distance, the ant seems to move in only one dimension, forward and back. But if you look closely, the cable itself has a circular cross-section, a second, tiny, curled-up dimension. Our entire universe could be a three-dimensional brain, a membrane floating in a higher dimensional space, with gravity potentially leaking into these extra dimensions, explaining why it feels so weak compared to the other forces. Another path is loop quantum gravity, which proposes that space itself is not smooth and continuous, but is woven from a fabric of tiny, discrete loops. This theory quantizes space and time directly, painting a picture of a universe built from a network of spinning threads. While it elegantly avoids the mathematical infinities that plague other approaches to quantum gravity, it has yet to show how Einstein's smooth spacetime emerges from this chaotic microscopic tapestry. How do we test these ideas? We look for subtle cracks in our current theories. Experiments constantly test the equivalence principle, the idea that all objects fall at the same rate in a gravitational field, a cornerstone of general relativity. Any tiny deviation could point toward new physics. When LIGO detects gravitational waves from colliding black holes, it is not just observing cosmic crashes, it is probing the very nature of gravity under the most extreme conditions, searching for any signature that betrays its quantum origins. The pursuit of unification is more than an abstract exercise. Unifying electromagnetism and the weak force led to predictions that eventually gave us the modern standard model of particle physics. A full theory of everything could reveal whether hidden dimensions are real, and it might unlock technologies we can scarcely imagine, perhaps even new forms of energy or propulsion. But to truly put these ideas to the test, we must look to the most extreme laboratories the universe provides, places where gravity becomes so overwhelming that it traps even light itself. These singularities represent the ultimate victory of gravity, a place where space-time curvature becomes infinite and our physical laws cease to make sense. At the very heart of a black hole, all the matter that ever fell in is crushed into a point of infinite density. According to Einstein's general relativity, that information, the unique configuration of every atom and particle, is irretrievably lost behind the event horizon, the point of no return. But quantum mechanics, the rulebook for the subatomic world, insists that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the sixth cosmic conundrum, the black hole information paradox, and it pits our two most successful theories of physics against each other in a fundamental conflict. The crisis was ignited by Stephen Hawking in the 1970s. He realized that the intense gravitational field just outside the event horizon could spontaneously create pairs of virtual particles. In a fleeting moment, a particle and its antiparticle pop into existence from the quantum foam, only to annihilate each other an instant later. But if this happens right at the edge of a black hole, one particle can fall in while the other escapes into space. The black hole loses a tiny amount of mass in the process. To an outside observer, the black hole appears to be emitting a faint glow of radiation, now known as Hawking radiation. Over unimaginable eons, this process would cause the black hole to slowly evaporate, eventually vanishing completely, and here lies the paradox. If the black hole evaporates and disappears, what happened to all the information about the stars, gas, and planets that fell into it? Did it simply vanish from the universe, violating a core principle of quantum mechanics? This is the problem of unitarity, the idea that the evolution of the universe must be predictable and information-preserving. For decades, physicists were deeply troubled. Was quantum mechanics wrong, or was general relativity incomplete? The most mind-bending resolution comes from the holographic principle, championed by theorists like Leonard Susskind. This idea suggests that all the information about what fell into a three-dimensional black hole is not lost inside, but is instead encoded on a two-dimensional surface, the event horizon itself. Think of it like a cosmic DVD. The movie you watch appears to have depth and motion in 3 dimensions, but all that information is actually stored on the flat, two-dimensional surface of the disk. In the same way, the event horizon could hold a scrambled hologram of every object that has ever crossed it. When Hawking radiation escapes, it slowly and chaotically carries that encoded information back out into the universe. The information was never truly lost, just locked in a form we cannot easily read. This idea finds a concrete footing in a theoretical framework called the AD-S/CFT correspondence. It proposes a perfect mathematical duality, a dictionary between a universe with gravity, like the space inside a black hole, and a quantum field theory without gravity living on its boundary. It is a powerful hint that gravity itself may be an emergent phenomenon, a consequence of quantum information processing on a lower dimensional surface. But this elegant solution brings its own shocking implication, the firewall paradox. If information is being released from the event horizon, does that mean the horizon is not the smooth, empty space Einstein predicted, but a searing wall of high-energy particles that would incinerate anything falling in? This remains a fierce debate. How can we possibly test such abstract ideas? The Event Horizon Telescope, which gave us the first image of a black hole's shadow, is not just taking pictures. By studying the polarized light around the event horizon of the supermassive black hole in the galaxy M87, it is probing the incredibly strong magnetic fields and chaotic environment where information transfer might be occurring. Furthermore, when gravitational wave observatories like LIGO detect the ripples from colliding black holes, they are recording the precise dynamics of spacetime itself. Sophisticated computer simulations of these mergers suggest that the final gravitational wave signal, the ring-down, might contain subtle imprints of the information preserved on the merged event horizons. If information is truly preserved, does that mean the fabric of spacetime is not fundamental, but woven from something deeper, from quantum entanglement and information itself? This paradox forces us to confront the very nature of reality, suggesting that our familiar dimensions of space and time are a projection from a world without them. As we grapple with information surviving the most destructive places in the cosmos, we must ask if anything can truly be eternal, or if even the vacuum of space itself is alive with change. Deep within the black hole's core, beyond the event horizon, lies a point where all predictions fail. This is the seventh cosmic conundrum, the nature of singularities. General relativity tells us that a star collapsing into a black hole, or the entire universe at the moment of the Big Bang, is crushed into a point of infinite density and zero volume. Space-time curvature becomes infinite, and the mathematics we rely on simply breaks down. A singularity is not a place you can visit. It is a sign that our current understanding of physics has reached its absolute limit. According to the groundbreaking singularity theorems of Roger Penrose, which earned him a Nobel Prize, these points are inevitable under the general conditions of Einstein's theory. If a certain amount of mass is compressed into a small enough space, gravity will always win, crushing matter into an infinitely dense point from which not even light can escape. The equations leave no room for escape, yet many physicists are deeply suspicious of these infinities. Nature, it seems, abhors a true singularity as much as it abhors a vacuum. This is where quantum theory is expected to come to the rescue, smoothing out the sharp edges of relativity. One compelling alternative comes from loop quantum gravity, which proposes that space itself is not infinitely divisible but is woven from a fabric of tiny, discrete loops. In this view, the crushing gravity of a collapsing star would eventually be met with a powerful quantum repulsion. Instead of collapsing to a point of infinite density, the star would bounce. The black hole singularity could be a gateway, a tunnel to a new region of spacetime, or perhaps even a new universe. This idea of a quantum bounce also applies to the Big Bang, suggesting our own universe may have been born from the collapse of a previous cosmos in an endless cyclic rhythm. String theory offers another fascinating alternative, the fuzzball. In this picture, there is no sharp singularity at the center of a black hole. Instead, the entire region inside the event horizon is filled with a tangled, vibrating ball of strings, a fuzzy, extended object with a complex, defined structure. The infinite density is replaced by a finite, though still unimaginably dense, state of matter. So how do we protect the sanctity of physics from these lawless points? This is the domain of the cosmic censorship hypothesis, which proposes that nature is polite enough to always hide its singularities behind an event horizon. In other words, a naked singularity, one exposed to the rest of the universe, can never form. This is a crucial conjecture because a visible singularity could lead to unpredictable paradoxes, perhaps even allowing for time travel by creating closed time-like curves, paths through spacetime that loop back on themselves. Computer simulations of collapsing stars are our digital laboratories, testing whether an event horizon always forms first, cloaking the impending singularity from our view. The search is on for any observational signature that could distinguish a traditional singularity from a fuzzball or a bounce. Do these points of infinite curvature represent the final boundary of our knowledge, or are they the very gateways that will lead us to the next great theory, the final piece of our cosmic puzzle, a complete theory of quantum gravity? These singularities are the starkest warning that our two pillars of physics cannot both be correct. For generations, physicists have faced a fundamental schism, a deep divide between the very large and the very small. This is the eighth cosmic conundrum, the relentless quest for quantum gravity. On one hand, we have general relativity, which paints a beautiful, continuous picture of space-time as a smooth, dynamical fabric warped by mass and energy. It perfectly describes the cosmic dance of planets, stars, and galaxies. On the other hand, quantum mechanics rules the microscopic world, a realm of probabilities, discrete packets of energy, and particles that behave like waves. It is a spectacularly successful theory for everything that happens inside an atom. But when these two worlds collide, in the first moments of the Big Bang or at the heart of a black hole, our equations produce nonsensical infinities. We are trying to write a play where two characters speak entirely different languages. The goal of quantum gravity is to teach them to converse, to rewrite the laws so that gravity emerges from the same quantum rules as every other force. Two primary visions dominate this pursuit. The first is loop quantum gravity, championed by physicists like Carlo Rovelli. This framework proposes that space itself is not smooth and continuous. Instead, it is woven from a fabric of tiny, discrete, indivisible loops. Picture the fabric of spacetime as a finely knitted sweater. From a distance, it looks like a single, continuous sheet. But if you could look with a magnifying glass of unimaginable power, you would see the individual threads and the tiny gaps between the stitches. In this view, the universe has a fundamental granularity, a smallest possible unit of space and time, preventing the infinite densities of singularities. The second grand vision is string theory. It suggests that the fundamental constituents of reality are not point-like particles, but incredibly small, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we see. A particular vibration corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force. But for the math of string theory to work, it requires more than the three spatial dimensions we experience. It posits extra dimensions, curled up into a space so infinitesimally small we never notice them, like the extra thickness of a tightly wound cable that an ant perceives only as a line. Beyond these two giants, other fascinating paths are being explored. The idea of asymptotic safety suggests that gravity might be a consistent quantum theory on its own, if its strength fades away at extremely high energies, making it manageable. Another radical proposal is that gravity is not a fundamental force at all. In scenarios of emergent gravity, space-time and its curvature might arise from something more primitive, like the quantum entanglement between particles. Think of the three-dimensional world you see on a hologram. It feels real, but it is actually projected from information stored on a flat, two-dimensional surface. In the same way, our four-dimensional universe of space and time could be a holographic projection from a quantum system with fewer dimensions. How can we possibly test these ethereal ideas? We look for subtle signatures in the most extreme laboratories the universe provides. When LIGO detects gravitational waves from colliding black holes, scientists meticulously analyze the signals, searching for any tiny deviation from Einstein's predictions that could hint at the quantum nature of gravity. We also look back in time to the very first moments after the Big Bang. The primordial gravitational waves that rippled through the infant universe, imprinted as a faint swirl in the cosmic microwave background, could carry the direct fingerprint of quantum gravitational effects. In laboratories here on Earth, physicists are building analog gravity systems using exotic states of matter, like Bose-Einstein condensates, to simulate black hole event horizons and study how Hawking radiation might behave. Even tabletop experiments that probe the fabric of spacetime at the tiniest scales could one day reveal a subtle graininess. Will quantum gravity ultimately reveal a universe built from discrete Lego-like blocks of spacetime? And if we can learn to manipulate those fundamental quanta, could it open doors to technologies beyond our wildest dreams, perhaps even new forms of quantum computing that harness the fabric of reality itself? This pursuit to unify the cosmos brings us back to its explosive beginning, forcing us to ask what could have set the entire cosmic story in motion with such perfect, precise force. That quest for a perfect, precise beginning leads us to a moment of almost unbelievable transformation. In the first sliver of a second after the Big Bang, the universe is thought to have undergone a growth spurt of staggering proportions, a process known as cosmic inflation. For a fleeting instant, space itself expanded faster than the speed of light, blowing up from a quantum speck to a volume far larger than our entire observable cosmos. This inflationary epoch is the proposed solution to some of the deepest puzzles we encountered earlier. It explains the horizon problem, how regions of the universe on opposite sides of the sky could have the same temperature even though they were never in causal contact. Inflation stretched a tiny, uniform patch to cosmic size, ironing out any initial wrinkles. It also solves the flatness problem, because this rapid expansion would have flattened the geometry of space, just as blowing up a balloon makes its surface appear flatter. But what could possibly power such an explosive event? The leading candidate is a hypothetical field dubbed the inflattened field. Think of it as a kind of cosmic engine, permeating all of space with a peculiar form of energy that generated a powerful repulsive gravity. As this field slowly rolled down its energy hill, it drove the exponential expansion, only stopping when it reached the bottom, its energy transforming into the hot soup of particles that would fuel the Big Bang. The physicist Andrei Linde took this idea even further with his concept of chaotic inflation. He proposed that inflation might not be a one-time event, but a natural and eternal process. In this view, different patches of the cosmos can randomly inflate at different times, creating a vast multiverse of bubble universes, each with its own unique physical laws. Our entire cosmos may be just one bubble in an infinite, frothing sea of universes. The most stunning evidence for inflation is written across the entire sky. The minute temperature variations in the cosmic microwave background, so meticulously mapped by the Planck satellite, are the direct descendants of quantum fluctuations. During inflation, the microscopic jitters of the inflattened field were stretched to astronomical sizes, creating the seeds of all future structure. The denser regions became the gravitational wells that would eventually pull in matter to form galaxies and clusters. We are essentially seeing the magnified quantum noise from the universe's birth. The ultimate confirmation of inflation, however, may lie in a specific type of ripple. As space expanded violently, it should have shaken the fabric of spacetime itself, generating primordial gravitational waves. These waves would have left a distinct curling pattern, a specific type of polarization, in the cosmic microwave background. Experiments are now scanning the sky for this faint signature, a B-mode polarization signal, which would be the smoking gun for inflation. So far, it has remained elusive, pushing scientists to refine their models and look deeper. This search forces us to confront profound questions about causality and our place in the cosmos. If eternal inflation is real, did our universe begin just once? Or is it one of countless beginnings in an endless cycle of creation? And if the very seeds of galaxies were sown by quantum chance, What does that say about the inevitability of our cosmic home? From these quantum seeds, amplified by inflation, the potential for everything we see began to take form, setting the stage for the first structures to emerge from the fading glow of creation. From the quantum seeds sown by inflation, a grand cosmic architecture began to assemble. This is the 10th great cosmic conundrum, the formation of the universe's large-scale structures. When we map the cosmos on its grandest scales, we do not see a random scattering of galaxies. Instead, we find a vast, intricate cosmic web, a network of brilliant galaxy clusters strung along dense filaments, separated by immense, dark voids of nearly empty space. This entire magnificent tapestry grew from the tiniest of beginnings, from those minute temperature fluctuations imprinted on the cosmic microwave background. For billions of years, gravity acted as the master sculptor, relentlessly amplifying these slight density variations. Where there was just a little more matter, gravity pulled in a little more from the surroundings, which in turn increased the pull in a powerful feedback loop known as gravitational instability. The dark matter we cannot see provided the gravitational backbone for this entire process, its invisible halos forming first and drawing in the normal, baryonic matter, the gas that would eventually light up as stars and galaxies. Our most powerful computers bring this epic story to life. Simulations like the Millennium Run model the evolution of a vast volume of the universe, tracing how dark matter clumps together in a process of hierarchical clustering. Small halos merge to form larger ones, which then assemble into galaxies, groups, and immense clusters, perfectly mirroring the patterns we observe in the real sky. How do we measure this cosmic web? One of our most powerful tools is a fossil imprint from the early universe called Baryon acoustic oscillations. In the first 400,000 years, the universe was a searing plasma of matter and radiation. Pressure waves like sound waves rippled through this hot soup, pushing matter outward in spherical shells. When the universe cooled enough for atoms to form, these waves froze in place, leaving a preferred scale of separation, a standard ruler etched into the fabric of space. By using enormous surveys like the Sloan Digital Sky Survey to measure the distribution of millions of galaxies, we can see this same scale reflected in the cosmic web today. It is a ruler we can use to measure the expansion history of the universe itself, but the story is not gravity alone. The normal matter adds its own dramatic chapters through powerful feedback. When massive stars explode as supernova, they blast outwards, heating and expelling galactic gas, which can stifle the birth of new stars. Even more immense are the active galactic nuclei, supermassive black holes at the centers of galaxies that unleash colossal jets of energy, heating the surrounding gas so thoroughly that it cannot cool and collapse to form stars. These processes self-regulate galaxy growth, preventing them from becoming too large too fast. Now, the James Webb Space Telescope is peering back to the era when the first strands of this web were being woven, observing early galaxies that are brighter and more structured than many models predicted. This challenges our understanding of how quickly gravity could have assembled such mature systems in the young cosmos. And looming over this entire narrative is the influence of dark energy. As the universe's expansion accelerates, dark energy is beginning to oppose the pull of gravity on the largest scales. It is stretching the cosmic web, slowing the growth of new clusters and making it harder for filaments to condense. We are living in the era when the universe's architecture is shifting from being dominated by gravity's construction to dark energy's dissolution. How does the specific shape of a galaxy's filamentary environment influence its evolution, determining whether it becomes a spiral or an elliptical? And as our maps of the cosmos become ever more detailed, could they reveal subtle, unseen patterns, imprints from physics even older than the Big Bang? This grand structure, from the vast voids to the brightest clusters, is all held in motion by gravity, a motion that first revealed the ghostly presence of dark matter through a simple, persistent anomaly in how galaxies spin. The grand cosmic web depends on a silent, unseen partner to hold it all together. This reliance was first exposed by a simple, persistent anomaly in the motion of stars. The 11th cosmic conundrum lies in the way spiral galaxies spin. According to the laws of gravity, stars orbiting on the outer edges of a galaxy should move much more slowly than those near the bright, dense center, just as Pluto orbits our Sun far more sluggishly than Mercury. But they do not. Observations reveal that stars and gas clouds in the distant outskirts whirl around at nearly the same high speed as those closer in. These flat rotation curves were the first definitive clue that galaxies are enveloped in massive, invisible halos of dark matter. The pioneering work of astronomer Vera Rubin provided the ironclad evidence. By meticulously measuring the Doppler shifts of light from stars and the radio waves from hydrogen gas clouds across different galaxies, she mapped their rotational velocities. The data was unequivocal. The outer regions were moving far too fast. The visible mass of stars and gas was simply not enough to supply the gravitational glue needed to prevent these galaxies from flying apart. Something else, something we could not see, was holding them together. This discovery forced a revolution in astrophysics. One proposed alternative is to question the law of gravity itself. A theory known as modified Newtonian dynamics, or MUND, suggests that on the incredibly low accelerations found in galactic outskirts, gravity behaves differently, becoming stronger than Newton's inverse square law predicts. For some specific galaxies, MUND can surprisingly reproduce their rotation curves without any dark matter at all. But for most scientists, the evidence for unseen mass is overwhelming. The way galaxy clusters behave, the precise bending of light by gravitational lensing, and the patterns in the cosmic microwave background all point to the existence of a new type of particle. Sophisticated computer simulations, known as N-body simulations, model the evolution of the universe with dark matter as a cold, collisionless fluid. These simulations successfully generate virtual galaxies with realistic rotation curves and large-scale structures that mirror our own cosmos. They rely on dark matter forming halos with specific density profiles, where the material is densest at the center. Yet here we find a fascinating tension, the core cusp problem. These simulations predict that dwarf galaxies, which are dominated by dark matter, should have a sharp peak, a cusp of high density in their centers. Instead, observations of many dwarf galaxies suggest their dark matter cores are much smoother and flatter. This is a potential crack in the prevailing model, a hint that dark matter might not be completely cold and collisionless, but could have some subtle, internal interactions we do not yet understand. Our own galactic neighbor, the Andromeda Galaxy, provides a perfect laboratory. Detailed maps of its rotation, built from tracking the motion of thousands of individual stars and gas clouds, show the same telltale flat curve, demanding a massive dark halo. The European Space Agency's Gaia mission is now refining these models to an unprecedented degree, precisely tracking the motions of over 1 billion stars in our own Milky Way. This vast stellar census is revealing the ghostly gravitational imprint of our galaxy's own dark matter halo in real time, and even suggesting that past collisions with smaller galaxies have left ripples in its distribution. Could dark matter be more complex than a single, simple particle? What if it is an entire hidden sector, with multiple particles and forces operating in a shadow universe parallel to our own? The search for a direct detection hinges on answering these questions. The anomaly in a galaxy's spin was our first glimpse of this profound cosmic secret, a ghostly hand guiding the dance of the stars. And as we sense this immense, invisible presence, we are drawn to the places where its influence becomes visible in the most dramatic way, where its gravity warps the very fabric of reality to create nature's own telescopes. That ghostly hand guiding the stars has left its fingerprints everywhere, and now we are building traps to catch it. The 12th cosmic conundrum is the direct search for dark matter particles, a global effort to move from observing the shadow to capturing the substance. This hunt takes us to some of the most isolated environments on Earth and far beyond. Deep within abandoned gold mines and under mountains, physicists have built ultra-sensitive laboratories shielded from the constant rain of cosmic rays. Here, in the profound silence and cold, they wait for a ghost to bump into something. The primary target for decades has been a class of hypothetical particles known as WIMP, or weakly interacting massive particles. The idea is elegant. These heavy particles would rarely interact with normal matter, but on the very rare occasion one passed through the detector, it could scatter off an atomic nucleus, producing a tiny flash of light or a minute amount of heat. To see such a faint signal, the detectors must be incredibly pure and kept at temperatures near absolute zero. Experiments like Xeno NNT in Italy and LUX Zeppelin, or LZ in the United States, use tons of liquefied xenon as their target. If a WIMP drifts through this vast tank, it might, with incredible rarity, knock into a xenon atom, causing it to scintillate with a telltale flash that sensitive cameras are waiting to catch. These experiments have grown exponentially in size and sensitivity, yet so far they have not found a definitive signal. Instead, they have set increasingly stringent limits, ruling out vast swaths of possible masses and interaction strengths for WIMP. This has pushed the frontier of the unknown ever further into the dark. Another compelling candidate is the action, a particle so light and wispy it was originally proposed to solve a different puzzle in particle physics. Actions would not bump into nuclei, but in the presence of a powerful magnetic field, they could theoretically convert into a faint microwave photon. Experiments like ADMCs are essentially giant, high-quality radio receivers, tuning through frequencies, listening for the whisper of an action converting into light. We also search for dark matter indirectly by looking for the debris it might leave behind. When two dark matter particles collide, they could annihilate each other, producing a spray of standard model particles like gamma rays. The Fermi Gamma Ray Space Telescope has mapped the sky in high-energy light, and one intriguing signal is an unexplained excess of gamma rays emanating from the center of our own Milky Way. Could this be the glow of dark matter annihilations? Dwarf spheroidal galaxies, which are tiny, ancient galaxies made almost entirely of dark matter, are also prime targets, as they offer a clean view without much contaminating astrophysical noise. The search extends to the highest energies on Earth, inside the Large Hadron Collider. By smashing protons together at nearly the speed of light, physicists hope to literally create dark matter particles in the debris. Since these particles would escape the detector without a trace, their presence would be inferred by an imbalance in momentum, a missing energy signature that points to something invisible carrying it away. Amidst all these null results, one experiment has claimed a potential signal for over 2 decades. The Dama/Libra experiment, located deep under the Gran Sasso mountain in Italy, uses crystals of sodium iodide. They report an annual modulation in their signal count rate, a slight rise and fall that peaks around June and dips in December. This, they argue, could be caused by Earth's motion through the galactic halo of dark matter, creating a wind that feels stronger in one season than another. Yet no other experiment using different materials has been able to reproduce this signal, creating a long-standing and contentious puzzle. The absence of clear signals has inspired theorists to explore wilder possibilities. Could dark matter be made of sterile neutrinos, heavier cousins of the standard neutrinos that interact only through gravity? Or could it be composed of primordial black holes, tiny black holes formed in the first second of the universe? The cosmic microwave background provides a powerful constraint, its precise patterns telling us that dark matter must have been slow-moving and cold in the early universe. Otherwise, the beautiful cosmic web we see today would not have formed. What if dark matter is not completely dark, but interacts with itself through a hidden force? This self-interacting dark matter could smooth out the dense centers of dwarf galaxies, potentially solving the core cusp problem, and would leave a different imprint on the formation of large-scale structure. This relentless hunt, with its cryogenic whispers and its silent waiting in the dark, shares a spirit with the mystery of fast radio bursts, those brilliant, unpredictable flashes from deep space. Both are cosmic detective stories where the clues are maddeningly faint and fleeting. The search for the particle identity of dark matter is more than a checklist of experiments. It is a fundamental inquiry into what makes up the bulk of our material reality. And as we listen for these phantoms in the dark, we are forced to ask if the greatest discoveries are not just about what we find, but about what we are compelled to invent when nature refuses to yield its secrets easily. While we listen for whispers from dark matter, the cosmos occasionally shouts with a voice of pure energy. In 2007, astronomers sifting through archived data from the Parkes Radio Telescope in Australia found something impossible: a single, brilliant flash of radio waves that lasted just 5 milliseconds yet packed more energy than our Sun emits in 80 years. This was the first detected fast radio burst, a cosmic conundrum so fleeting and powerful it seemed to defy explanation. These bursts are not the slow burn of a star, but the brief, intense crackle of a cosmic spark, arriving from so far away that their sources must be among the most energetic events in the universe. The initial discovery by Duncan Lorimer and his team was met with deep skepticism. Could such a signal be real, or was it just terrestrial interference, a microwave oven in the observatory kitchen perhaps? But then more were found, confirming we were witnessing a genuine and profound astrophysical mystery. What kind of object can produce such a staggering release of energy in the blink of an eye? The plot thickened when we discovered that some of these bursts are one-off explosions, while others, like FRB 121102, repeat, flashing again and again from the same patch of sky. This simple fact of repetition immediately ruled out cataclysmic, self-destructive sources for at least some of them, like the merger of two neutron stars. The repeating bursts pointed toward a source that could survive its own violent outburst, a rapidly spinning, highly magnetized neutron star known as a magnetar. These stellar corpses possess magnetic fields so intense they could strip the information from a credit card from a distance halfway to the moon. A star quake on a magnetar's surface, a sudden cracking of its rigid crust, could unleash a firestorm of radio waves fitting the profile of a fast radio burst perfectly. Yet the diversity of the signals suggests we are dealing with more than one type of culprit. Theories abound, from the tidal disruption of an asteroid by a neutron star to the tumultuous interactions within a young, energetic nebula. Some have even dared to speculate about artificial origins, engineered beacons from advanced civilizations. While this is a thrilling thought, the scientific consensus firmly favors natural, if extraordinarily violent, astrophysical engines. Beyond their mysterious origins, these bursts have become unexpected tools for cosmic cartography. Each burst travels for millions or even billions of years to reach us, and on its journey, It passes through the diffuse clouds of electrons that fill the space between galaxies. This leaves a distinct fingerprint on the signal called the dispersion measure. The higher frequencies of the burst arrive at our telescopes just a fraction of a second before the lower frequencies. By measuring this delay, astronomers can count the total number of electrons the burst encountered along its path, effectively weighing the invisible matter in the cosmic web. It is like using a flash of lightning to illuminate the structure of a distant storm. Polarization studies add another layer of intrigue. When the radio waves from some bursts are polarized, their electric fields aligned in a specific way, it tells us they have passed through powerful magnetic fields, hinting at the ferocious environment that spawned them. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are revolutionizing the field. With its stationary array of metal mesh, CHIME acts like a wide-angle camera for the radio sky, discovering hundreds of new bursts and pinpointing many to their host galaxies, which range from distant dwarfs to massive spirals. This localization is crucial as the type of galaxy can point to the nature of the source. Could these brilliant flashes be cosmic lighthouses, revealing not just the structure of the universe, but also new states of matter or fundamental physics we have not yet discovered? They illuminate the vast, magnetized plasma that constitutes most of the visible universe, a sea of charged particles we are only beginning to understand. And just as these bursts are the universe's most brilliant radio flashes, there are other messengers, cosmic rays, that arrive as silent, ultra-high-energy bullets, each one a conundrum of its own. These brilliant radio flashes share the cosmos with another, even more elusive messenger. Arriving from the depths of space are atomic nuclei traveling at nearly the speed of light, each one a bullet of pure energy. This is the 14th cosmic conundrum, the mysterious source of ultra-high-energy cosmic rays. A single one of these particles can carry the kinetic energy of a professionally thrown baseball, all compressed into a subatomic fragment. Their energies soar beyond 10 to the 18 electron volts, making them millions of times more powerful than anything we can produce in the Large Hadron Collider. They are the fastest things in the universe, yet we have no idea what cosmic cannon is firing them. When such a particle, often a lone proton or the nucleus of an iron atom, slams into our upper atmosphere, it triggers a spectacular air shower. This cascade of secondary particles rains down over an area the size of a small city, creating a faint, fleeting glow of ultraviolet light that specialized telescopes can detect. The Pierre Auger Observatory in Argentina, an array of over 1,600 water tanks spread across 3,000 square kilometers, acts as a giant catcher's mitt for these showers. By combining the tank data with fluorescence telescopes that see the faint atmospheric glow, it pieces together the energy, direction, and identity of the primary particle. The data reveals a crucial clue: anisotropy. These ultra-high-energy events are not perfectly random. They show a faint statistical preference for arriving from certain directions in the sky, pointing away from the plane of our own Milky Way. This tells us their accelerators must be extragalactic, lying far beyond our galactic neighborhood. But which extragalactic monsters are capable of such a feat? The suspects are the most violent engines in the universe, active galactic nuclei, where a supermassive black hole feasts on matter and blasts out jets of plasma, could potentially focus and accelerate particles to these insane energies. Cataclysmic gamma-ray bursts, the birth cries of black holes or the collisions of neutron stars, are another prime candidate. The mechanism thought to be at work is a natural version of a particle accelerator called Fermi shock acceleration. Imagine a subatomic particle trapped between two approaching magnetic shock fronts. much like a ping-pong ball being volleyed back and forth faster and faster between two swinging paddles. Each crossing of the shock front gives the particle a small boost of energy, and over thousands of cycles, it gains astronomical speed. This process is believed to occur in the expanding shock waves of supernova remnants, though whether it can explain the very highest energies remains a subject of intense debate. The journey of these particles is just as important as their launch. They do not travel in straight lines. The tangled magnetic fields that permeate the cosmos act like a funhouse hall of mirrors, bending and scattering the paths of these charged particles until their arrival direction bears little resemblance to their true point of origin. This magnetic scrambling is a primary reason why pinpointing their sources has been so frustratingly difficult. There is also a fundamental speed limit for these cosmic travelers, known as the Giesecke cutoff. A proton with an energy above about 10 to the 20 electron volts should not be able to travel very far through the universe. It will inevitably collide with a photon from the cosmic microwave background, the relic radiation from the Big Bang. In this collision, the proton loses a tremendous amount of energy, creating a new particle called a pion. This process effectively means that any ultra-high-energy cosmic ray we detect must have originated within a relatively local volume of the universe, perhaps within a few 100 million light-years. The fact that we see particles with energies beyond this cutoff is a puzzle in itself, suggesting either that the sources are very nearby on the cosmic scale, or that our understanding of particle physics at these extreme energies is incomplete. The modern hunt relies on multi-messenger astronomy. The dream is to catch an ultra-high-energy cosmic ray at the same time and from the same direction as a neutrino or a gamma-ray flare. A neutrino, being neutral and unaffected by magnetic fields, would travel in a straight line pointing directly back to the source. Such a correlation would be the smoking gun. What extreme environments can withstand the immense magnetic and kinetic pressures required to accelerate a particle to such a velocity? Could these particles be the byproduct of exotic physics, such as the decay of super-heavy dark matter particles from the early universe? This mystery is deeply intertwined with the enigma of gamma-ray bursts, as both phenomena push the limits of energy and force us to ask if we are witnessing the same cosmic engines through different lenses. These silent, ultra-high-energy bullets are sometimes the harbingers of the universe's most violent detonations. Gamma-ray bursts are the most powerful explosions we have witnessed since the cosmos itself began, brief flashes of gamma-ray light that can outshine every star in the universe combined for a few fleeting seconds. They are the 15th cosmic conundrum, cosmic beacons signaling the death of massive stars or the catastrophic merger of the densest objects known. For decades after their accidental discovery by military satellites, their origin was one of astronomy's greatest secrets. Were they local within our galaxy or from the farthest reaches of space? The answer came from missions like Neil Gerald's Swift Observatory, which could rapidly swivel to catch the fading afterglow of a burst in X-ray, ultraviolet, and optical light. By pinpointing these afterglows to distant galaxies, we learn these are truly extragalactic events occurring billions of light-years away, which means their intrinsic power is almost unimaginable. We now classify them into two broad families based on their duration. Short gamma-ray bursts last less than 2 seconds and are now strongly linked to the merger of two neutron stars, or a neutron star and a black hole. Long gamma-ray bursts last longer than 2 seconds and are associated with the core collapse of a rapidly spinning, massive star into a black hole, an event known as a hypernova. The engine for both is phenomenally powerful. In a long burst, as the star's core collapses, it can form a newborn black hole that rapidly devours the surrounding stellar material. This creates an accretion disk of superheated gas, and along the star's rotation axis, it can blast out jets of plasma at over 99.9% the speed of light. These are relativistic jets, and if one of them is pointed fortuitously at Earth, we see the brilliant flash of a gamma-ray burst. The short bursts have a different but equally dramatic origin. Confirmation arrived on August 17, 2017. The LIGO and Virgo gravitational wave observatories felt the distinct space-time ripple of two neutron stars colliding. Just 2 seconds later, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same region of sky. This multi-messenger event, known as GW 170817, was a watershed moment. It proved unequivocally that neutron star mergers produce both gravitational waves and short gamma-ray bursts. The aftermath of such a merger is a cosmic gold factory. The event creates a kilonova, an explosion that forges heavy elements through a process called rapid neutron capture, or the R process. The intense neutron-rich environment sprays out vast amounts of gold, platinum, and uranium, seeding the cosmos with the very elements that make up our jewelry and power our nuclear reactors. A single merger can forge hundreds of times the Earth's mass in gold. These bursts are so luminous they can be used as standard candles to probe the distant universe, helping us measure cosmic distances and the expansion rate. Yet their power raises a sobering question. Could a nearby gamma-ray burst pose a threat to life on Earth? A burst within our own galaxy, and pointed directly at us, would likely strip away the ozone layer, triggering a mass extinction. Fortunately, the rate of such events in the Milky Way is low, and the jet must be precisely aligned, making it a cosmic danger, but a statistically remote one. What do these brilliant, destructive flashes tell us about the lives and deaths of stars? They are the ultimate signposts of stellar transformation, the violent endpoints that create black holes and scatter the elements of life across the galaxies. And the incredible magnetic fields that channel and focus their relativistic jets hint at a deeper, pervasive force shaping the cosmos from within. These brilliant jets and explosive mergers are sculpted by an invisible cosmic force, one that threads through the void and weaves through every galaxy. The 16th cosmic conundrum is the origin and evolution of cosmic magnetic fields. These fields are not confined to stars and planets. They are vast, interstellar ghosts, stretching for tens of thousands of light years, influencing how stars are born and guiding the paths of those ultra-high-energy cosmic rays. We see their handiwork everywhere, in the polarized glow of synchrotron radiation from the jets of active galaxies, where electrons spiral at near light speed around magnetic field lines. We map their strength and direction through a clever trick of nature called Faraday rotation. As polarized radio waves travel through the magnetized plasma of interstellar space, the magnetic fields slowly twist the polarization angle of the waves. By measuring this celestial fingerprint, astronomers can chart the invisible magnetic architecture of our own Milky Way and beyond. But where did these fields come from in the first place? The initial seed could have been incredibly weak, a faint whisper in the primordial cosmos. One idea is that they were born from tiny imbalances in the earliest moments, perhaps during the inflationary epoch or from violent phase transitions as the fundamental forces of nature split apart. These minuscule seeds then needed a cosmic engine to grow. That engine is the dynamo effect. Think of a dynamo as a self-exciting generator operating on a galactic scale. As turbulent plasma, stirred by supernova explosions and the rotation of the galaxy, moves through an existing weak magnetic field, it stretches and twists the field lines, amplifying them tremendously. It is like stirring a cup of coffee with a tiny magnet inside. the motion can generate a measurable magnetic field. Our most powerful supercomputers run magnetohydrodynamic simulations to recreate this epic amplification, and they successfully produce the large-scale magnetic structures we observe, winding through the spiral arms of galaxies like our own. These fields are not passive observers, they are active players in the cosmic drama. They help confine cosmic rays, trapping those high-energy particles within the galaxy and making them bounce back and forth for millions of years. They also influence the very collapse of gas clouds to form new stars, providing a form of support against gravity that can slow down the star formation process. There are even speculative links to dark matter, as the presence of magnetic fields could influence where and how dark matter particles might annihilate, potentially altering the signals we hope to detect. The search for the most ancient magnetic fields takes us back to the cosmic microwave background. The Planck satellite hunted for a specific signature of primordial magnetism in the polarization of this ancient light. So far, no definitive signal has been found, telling us that any original fields from the Big Bang must have been exceptionally faint. Could magnetic fields be a fundamental relic from creation itself, as foundational to the cosmos as matter and radiation? And how does their silent, pervasive pressure help sculpt a galaxy's destiny, from its first gas clouds to its final stellar population? This intricate dance of invisible forces shaping the visible universe reminds us that our measurements of cosmic expansion itself may be influenced by subtleties we are only beginning to grasp. Our most precise measurements of cosmic expansion are now telling two different stories. This is the 17th great cosmic conundrum, the Hubble-constant-tension, a growing rift at the very heart of modern cosmology. The Hubble constant is the number that tells us how fast the universe is expanding today, the current expansion rate. For decades, astronomers have worked to pin down its exact value, but we are now faced with a stubborn and significant discrepancy. One method involves peering back in time to the infant universe, using the pristine snapshot of the cosmic microwave background from the Planck satellite. By applying our well-tested model of cosmology, we can predict what the expansion rate should be today. This early universe method gives us a value of about 67 kilometers per second per megaparsec. Yet, when we measure the universe locally using a cosmic distance ladder, we get a different answer. This ladder is built step by step, starting with pulsating stars called Cepheid variables in nearby galaxies, whose known brightness allows us to gauge distances, which we then use to calibrate the brightness of more distant supernovae. This local measurement, championed by Nobel laureate Adam Rees and his team using the Hubble Space Telescope, consistently gives a value of around 73. The difference seems small, just a few kilometers per second, but the uncertainty in both measurements has shrunk to the point where this gap is now statistically significant, a genuine tension that cannot be easily ignored. As Rees has stated, the probability that this is a fluke is exceedingly small, maybe 1 in a million. This is not just a minor calibration issue, it is a potential crack in the foundation of our standard model of cosmology, lambda CDM. Could this tension be a clue to new physics? One compelling idea is early dark energy, a theoretical form of dark energy that could have been active in the universe's first few 100,000 years. This extra push would have subtly altered the conditions imprinted on the cosmic microwave background, changing the predicted expansion rate today to better match what we see locally. Other theories suggest that dark energy is not a constant but an evolving fluid, or that dark matter and dark energy interact in ways we have not yet considered. There is also the possibility that neutrinos, those ghostly particles, have unexpected properties that could resolve the conflict. a new and completely independent method is now entering the fray: gravitational wave standard sirens. When LIGO and Virgo detect the ripples from colliding neutron stars, they provide a direct measure of the distance to the event without needing a cosmic ladder. The first such standard siren from the event GW170817 gave a value that intriguingly leaned toward the higher local measurement. This independent check is crucial as it helps rule out hidden systematic errors in the traditional methods, yet the tension persists, intertwining with other cosmic puzzles. The predicted abundance of lithium from the Big Bang is also lower than what we observe, another small but persistent anomaly that suggests our model of the primordial universe is still incomplete. Is this discrepancy a sign that we need to rewrite the textbooks, introducing new components or revising fundamental laws? Or is it a final, stubborn systematic error that will eventually be resolved with more precise data from the James Webb Space Telescope and next-generation observatories? The Hubble constant is more than just a number. It is the ultimate benchmark for the age, size, and fate of our universe. This tension is not a failure of science, but a thrilling sign that we are on the verge of a deeper understanding, a moment where the cosmos is challenging us to look closer and think harder about the fabric of reality itself. That same stubborn tension in our cosmic measurements echoes in the very elements forged at the dawn of time. Among the first atoms created in the fiery furnace of the Big Bang, one element stands out as an anomaly, a note that rings slightly flat in an otherwise harmonious prediction. This is the 18th cosmic conundrum, the cosmological lithium problem. In the universe's first 20 minutes, a process known as Big Bang nucleosynthesis cooked up the primordial soup of light elements. The theoretical calculations for the amounts of hydrogen, helium, and their isotopes are a spectacular success story, matching observations of the oldest cosmic gas clouds with breathtaking precision. All except for one, lithium-7. The models predict that this specific isotope of lithium should be about 3 times more abundant in the oldest stars than what we actually observe. It is a persistent deficit that has puzzled cosmologists for decades. Where did all the lithium go? The search for an answer takes us deep into the heart of nuclear physics. The initial fusion reactions in the Big Bang were a frantic race against time as the universe expanded and cooled. The predicted amount of lithium hinges on the precise rates of a chain of nuclear reactions, their probabilities known as cross-sections. Physicists like Brian Fields have meticulously explored whether the solution lies in a previously unknown resonant reaction, a kind of nuclear shortcut that could have destroyed lithium-7 more efficiently in the early universe. Minute uncertainties in these laboratory-measured cross-sections could be the key to unlocking the mystery. To test this, nuclear physicists use particle accelerators like Canada's Triumph facility, attempting to recreate the conditions of the Big Bang nucleus by nucleus, smashing beams of particles into targets to measure these elusive reaction rates with ever greater precision. Yet, even with refined data, the lithium shortfall persists, leading some to wonder if exotic new physics is at play. Could decays of hypothetical particles from supersymmetry have altered the nuclear reaction network in those first few minutes? Or could dark matter particles have interacted with the primordial plasma, subtly shifting the balance of elements? The alternative is that the lithium was made correctly, but then it disappeared. Perhaps stellar processes are to blame. We observe this lithium discrepancy in ancient, metal-poor stars in the halo of our galaxy, the stellar fossils of the early cosmos. These stars are our cleanest laboratories. Using powerful telescopes like the Very Large Telescope in Chile, astronomers perform delicate spectroscopic surveys, splitting the faint light from these ancient suns to read their chemical composition. The consistent lack of lithium suggests these stars might be destroying it. As these stars churn and rotate, their surface lithium could be dragged down into hotter interior layers where it is fused into heavier elements. But modeling this depletion is complex, and it is unclear if the process is efficient enough to account for the entire deficit. This puzzle is more than a minor accounting error in the cosmic ledger. Lithium is a crucial piece of the story of how the first elements formed, the raw material for the first stars and planets. Its anomalous behavior is a direct probe of physics in the universe's first moments, a window into a realm far beyond the reach of any particle collider. If the solution involves new particles or forces, it would reshape our understanding of the fundamental interactions that govern creation. And since lithium is an element used in the technology of advanced civilizations, its cosmic abundance touches upon the very prerequisites for life. Could the resolution of this elemental mystery also reveal something about the likelihood of life arising elsewhere in the cosmos? This elemental imbalance, forged in the first moments, is a direct echo of the profound asymmetry that allowed our material world to exist at all. That profound elemental imbalance, the very lithium missing from our oldest stars, reminds us that the ingredients for life are scattered unevenly across the cosmos. This leads us to a haunting silence, the 19th cosmic conundrum, the Fermi-paradox. Physicist Enrico Fermi, during a casual lunch conversation in 1950, posed the question that has echoed through the decades: if the universe is so vast and old, where is everybody? The numbers seem to be on the side of life. Our Milky Way galaxy alone contains hundreds of billions of stars, and many of these are now known to host planets. Data from the Kepler Space Telescope suggests there could be billions of Earth-sized worlds orbiting within the habitable zones of their stars, that Goldilocks region where temperatures are just right for liquid water to exist. With such staggering statistics, the galaxy should be a bustling metropolis of civilizations, its lanes buzzing with interstellar traffic. Yet when we listen, we are met with a profound and unsettling quiet. This is the Great Silence. For over 60 years, projects like SETI, the search for extraterrestrial intelligence, have scanned the skies for artificial radio signals. Pioneers like Jill Tarter devoted their careers to this search, sifting through the cosmic static for a pattern that shouts, "We are here." Modern efforts like Breakthrough Listen use some of the world's most powerful radio telescopes to monitor millions of nearby stars, expanding the search to include laser pulses and other technosignatures. So far, the airwaves have been silent. The Drake equation provides a framework for this puzzle, multiplying factors from the rate of star formation to the fraction of planets that develop life, and crucially, the average lifetime of a technological civilization. It is in these unknown variables that the paradox finds its possible resolutions. Perhaps the Great Silence means the cosmos is a much more dangerous place than we realized. This is the core of the Great Filter hypothesis, which suggests that there exists at least one nearly insurmountable barrier that prevents life from advancing to the stage of interstellar communication. The filter could lie in our past. Maybe the spontaneous origin of life, abiogenesis, is an astronomically rare fluke, a spark of complexity so unlikely that we are the only ones to have caught fire in our galactic neighborhood. Or perhaps the filter is the leap from simple single-celled life to complex multicellular organisms, a transition that took billions of years on Earth. The more chilling possibility is that the great filter lies in our future. It could be that almost all technological civilizations inevitably destroy themselves, whether through nuclear war, engineered pandemics, or a climate catastrophe of their own making. The longevity term in the Drake equation would then be tragically short. Other solutions are less grim but equally mind-bending. The zoo hypothesis proposes that advanced civilizations are aware of us, but have chosen to place us in a kind of cosmic quarantine, observing from a distance to allow our natural, cultural, and biological development. Or perhaps interstellar travel is simply too slow, too expensive, or too pointless for any society to undertake on a galactic scale. The vast distances between stars may be the ultimate prison walls. Our search is now broadening. We are not just listening for radio signals, but looking for other signs of technology. Could we detect the light from city nights on a distant exoplanet, or the waste heat from a Dyson sphere harvesting a star's energy? The mysterious interstellar object Oumuamua, which passed through our solar system in 2017, sparked intense debate precisely because its unusual acceleration could not be easily explained by natural causes, though most scientists attribute it to outgassing. Its very existence, however, tells us that material from other star systems is constantly drifting by, and some of it might one day carry a deliberate message. Are we alone in a dead, mechanistic universe, or are we simply too primitive to recognize the forms that advanced intelligence might take? Could other civilizations have transitioned to a post-biological state, existing as pure information within vast computational networks, invisible to our crude radio telescopes? This profound silence forces us to look inward, back to our own planet, to confront the deepest mystery of all. How did lifeless chemistry first awaken into biology? That profound silence in the cosmos brings the question of life's origin into sharp focus. The transition from non-living chemistry to a self-replicating organism is perhaps the most intimate of all cosmic mysteries, the 20th conundrum, abiogenesis. How did inanimate matter first awaken into biology on our planet? And is this a process written into the laws of the universe? The classic experiment by Stanley Miller and Harold Urey in the 1950s provided the first stunning clue. They recreated the hypothesized conditions of early Earth in a flask, with a primordial atmosphere of water, methane, ammonia, and hydrogen, zapped by electrical sparks to simulate lightning. Within days, the clear water turned a murky pink and brown, and analysis revealed it was rich in amino acids, the fundamental building blocks of proteins. This was a revelation, proving that the basic ingredients for life could form spontaneously from simple chemistry. But going from a soup of amino acids to a self-replicating system is a leap of staggering complexity. One leading hypothesis is the RNA world, a time before DNA and proteins, when RNA ruled the early Earth. RNA is a remarkable molecule. It can store genetic information like DNA, but it can also act as an enzyme, catalyzing chemical reactions, including copying itself. In this view, the first spark of life might have been a fragile, self-replicating strand of RNA emerging in a protected environment. Where could such a delicate process begin? Deep-sea hydrothermal vents are a compelling candidate. These are not the scorching black smokers, but cooler alkaline vents like the Lost City Field, with porous, chimney-like structures rich in minerals. These mineral surfaces could have acted as both catalysts and templates, concentrating organic molecules and fostering the formation of ever more complex chains, effectively serving as the first primitive cells. The alternative idea of panspermia suggests we should not limit our search to Earth alone. Perhaps the seeds of life are universal, and life's building blocks, or even dormant microbes, are hitchhiking across the galaxy on comets, asteroids, and interstellar dust. The Murchison meteorite, which fell in Australia in 1969, was found to be packed with over 90 different amino acids, many of which are not common on Earth, proving that the chemistry for life is actively occurring in space. In laboratories, scientists simulate the cold, dark clouds of interstellar space, bombarding icy mixtures with radiation, and find that they readily form nucleobases, the letters of the genetic code, and even the complex structures of cell membranes. To test these ideas, we look for life in the most extreme environments on Earth, places we once thought were sterile. Microbes called extremophiles thrive in boiling acid, in the crushing pressures of the deep ocean, and in rocks deep beneath the surface. If life can flourish here, it could potentially survive in the subsurface ocean of Jupiter's moon Europa or in the salty seeps of Mars. Our rovers are now actively drilling into Martian rock, analyzing samples for any chemical signature, any fossil imprint that would indicate life once took hold on our neighboring world. Is life a cosmic imperative, an inevitable outcome of chemistry and planetary conditions given enough time? Or is it a statistical fluke, a miracle of such improbability that we are truly alone? The answer lies in the intricate dance of molecules and energy that transforms a barren world into a living one, a story that begins with the very formation of the planets themselves. From the chemistry of life's origins, we arrive at the cosmic forges where worlds themselves are born. The 21st cosmic conundrum is the mechanism of planet formation, a process of breathtaking violence and delicate balance unfolding within the swirling disks of gas and dust that surround infant stars. These protoplanetary disks are the cradles of solar systems, and within them, microscopic dust grains must perform an intricate dance to grow from mere specks into full-fledged planets. The first step seems simple enough. Tiny particles of dust and ice stick together through static electricity, forming fluffy aggregates, but this growth hits a catastrophic wall known as the meter-size barrier. At this scale, objects are in a dangerous limbo, too large to be held in place by the disk's gas pressure, but too small for their own gravity to be significant. They are caught in a headwind that saps their orbital energy, causing them to spiral into the star within a few hundred years, a cosmic death sentence before a planet can ever form. So how do planets overcome this barrier? One elegant solution is pebble accretion, championed by theorists like Andrew Youden. Imagine a larger, kilometer-sized planetesimal moving through a disk filled with tiny pebbles. Its gravity acts as a net, efficiently sweeping up these smaller objects. This process allows for incredibly rapid growth, potentially building the core of a giant planet in just a few thousand years instead of millions. Our most powerful observatory for studying this nursery is the Atacama Large Millimeter/Submillimeter Array, or ALMA. Its stunning images of disks around stars like HL Tauri reveal a series of bright and dark rings, gaps, and spiral arms. These are not simple smooth disks, they are structured, with planets likely already carving their paths through the primordial material, clearing their orbits as they grow. This leads to the two main theories for how giant planets form. The core accretion model is a bottom-up process, where a solid core of rock and ice forms first, and once it reaches a critical mass of about 10 Earths, it begins rapidly pulling in a massive envelope of hydrogen and helium gas. This is likely how Jupiter and Saturn were born. The competing idea is disk instability, a top-down scenario where a massive, cold disk of gas suddenly fragments under its own gravity, directly collapsing into a giant planet. This could explain worlds that orbit very far from their stars, but a young planet's journey is far from over. Through gravitational interactions with the disk, planets can migrate inward, spiraling dangerously close to their host star. This process may explain the existence of hot Jupiters, giant worlds orbiting perilously close to their suns. Migration also plays a crucial role in delivering the ingredients for life. In our own solar system, the Grand TAC model suggests a young Jupiter migrated inward, then back out, scattering icy material from the outer system toward the inner terrestrial planets, delivering the water that now fills our oceans. Data from the Kepler telescope reveals the demographics of this cosmic population. We now know that small, rocky planets are incredibly common, perhaps outnumbering stars in our galaxy. Yet an Earth-like planet in size and orbit is only the first condition for habitability. A world must also hold onto its atmosphere, a delicate balance against the relentless stellar wind and radiation from its star. The TRAPPIST-1 system, with its 7 Earth-sized worlds, showcases this diversity, with some planets potentially being water worlds and others having lost their atmospheres entirely. We have even begun to directly image alien worlds, with systems like HR 8799 showing 4 giant planets captured as faint points of light orbiting their star, a direct snapshot of a young planetary family. So how common is a world like ours with its stable orbit, protective magnetic field, and life-nurturing oceans? The sheer number of small planets suggests the raw materials are abundant, but the precise sequence of events that built our pale blue dot may be a rare and intricate symphony. This search for our own planetary origins inevitably leads us to look closer to home, to the strange and ancient puzzles locked within our own solar system's family. Our own cosmic backyard holds ancient scars of a violent and dynamic past. The 22nd cosmic conundrum lies in the strange anomalies of our solar system, peculiarities that suggest our familiar planetary family was forged in chaos. The planets orbit the Sun in a neat, flat plane, but beyond Neptune, in the frozen realm of the Kuiper belt, many objects follow wildly tilted and eccentric paths, clustered in a way that should not happen by chance. This strange orbital architecture is one of the strongest hints for a yet unseen world, a hypothetical planet 9. This would not be a small rock, but a super-Earth with a mass up to 10 times our own planet, tracing a vast elliptical orbit far beyond Pluto. Its immense gravitational pull, theorists like Konstantin Batygin propose, could be shepherding these distant icy bodies into their strange, clustered orbits. Finding this ghost world, however, is a monumental challenge, as its proposed orbit takes it so far from the Sun that its reflected sunlight is vanishingly faint. This potential hidden planet is just one piece of a much larger puzzle, the story of our solar system's turbulent youth. The leading narrative for this chaos is the Nice model, named for the city in France where it was developed. This theory posits that our giant planets Jupiter, Saturn, Uranus, and Neptune did not form in their current positions. They began in a much more compact configuration, nestled closer together. Over time, gravitational jostling sent them drifting, in a grand reshuffling that scattered comets and asteroids across the system. This period of migration may have triggered the late heavy bombardment, a cataclysmic era around 4 billion years ago when the inner planets were pummeled by a rain of impactors, leaving behind the cratered landscapes we see on the Moon and Mercury today. The extreme tilt of Uranus, which spins on its side, is another fossil from this time, likely the result of a colossal collision with an Earth-sized protoplanet. We are now gathering direct evidence of these ancient events. The New Horizons spacecraft's flyby of the Kuiper Belt object Arakoth provided a stunning snapshot of the solar system's primordial building blocks. Its two-lobed snowman shape shows that planetesimals formed gently through the slow merging of smaller bodies, not through violent collisions. Meanwhile, the Juno mission's precise measurements of Jupiter's gravity field revealed a surprisingly fuzzy core, suggesting the giant planet may have absorbed a massive planetary embryo early in its history, or that its core has been slowly eroded over billions of years. Even the Sun itself holds a clue. Its composition is subtly different from the inner planets, suggesting material was sorted and separated during that early, dynamic period. Where did all the material for the Oort cloud, that distant spherical shell of trillions of comets, actually come from? It is too far away to have formed in place. The leading idea is that it was built from icy planetesimals that were flung outwards by the gravity of the migrating giant planets, their orbits stretched by the gentle pull of passing stars and the tidal forces of the Milky Way galaxy itself. And closer to home, the Moon's origin remains a defining mystery. The prevailing giant impact theory suggests a Mars-sized body, often called Theia, slammed into the young Earth, vaporizing a portion of our planet and hurling a disk of molten debris into orbit that later coalesced into our Moon. This explains the Moon's surprisingly low density and its similar isotopic composition to Earth, but the precise details of that apocalyptic collision are still being refined. Could there be other, even more ancient relics hiding in the darkness, perhaps a primordial black hole or a captured rogue planet from another star system? And as we discover moons around distant exoplanets, we are forced to ask if our own solar system's chaotic formation is the rule or a rare exception. These local anomalies are a direct window into the universal processes of planetary birth and evolution, reminding us that even the most familiar places can hold the deepest cosmic secrets. A world orbiting a world bathed in the reflected light of a foreign sun could be the most common abode for life in the universe. The 23rd Cosmic Conundrum takes us beyond exoplanets to the tantalizing search for exomoons. If our own solar system is any guide, where moons outnumber planets by a vast margin, these distant satellites may be the true jewels of other star systems. Yet spotting a tiny moon circling a planet that is itself a mere speck next to its brilliant star is a challenge that pushes our observational skills to the absolute limit. The primary method relies on exquisitely precise timing. As a planet transits or passes in front of its star, a large moon's gravity will cause a subtle wobble. The planet may start its transit a few minutes early or late, a phenomenon called a transit timing variation, or the transit's duration might itself change, a transit duration variation, as the planet and moon swing around their common center of gravity. It is like trying to detect a fly buzzing around a gnat by the tiny shadow they cast together against a distant searchlight. Leading this frontier is astronomer David Kipping and his hunt for exomoons with Kepler project. His team meticulously analyzed data from the Kepler Space Telescope, and one candidate, Kepler 1625b, captured global attention. Observations from the Hubble Space Telescope suggested a second, smaller dip in starlight following the planet's own transit, a potential signature of a Neptune-sized moon. The statistical evidence remains contentious, highlighting the immense difficulty of separating a true moon signal from stellar noise or instrumental artifacts. The reward for this painstaking work, however, could be immense. An exomoon, especially one around a gas giant in the habitable zone, could be a paradise. While the planet itself would be a hostile ball of gas, its moon might have a solid surface, bathed in gentle stellar warmth. More intriguingly, tidal heating could provide a powerful internal energy source. Just as Jupiter's gravity stretches and squeezes Io, making it the most volcanically active body in our solar system, a similar gravitational tug of war could keep a distant exomoon's subsurface ocean liquid for billions of years, completely independent of starlight. Our own solar system offers compelling analogues. Europa's hidden global ocean and Titan's thick atmosphere and liquid methane lakes show that moons can be worlds in their own right, with complex chemistry and potential habitats. When we search for exomoons, we are essentially looking for more Europas and Titans, but orbiting alien suns. The next great leap will come from the James Webb Space Telescope. Its unparalleled sensitivity may allow it to detect the atmospheric signatures of exomoons directly. By analyzing the combined starlight filtering through both a transiting planet and its large moon, we might one day identify biosignatures like oxygen or methane in a lunar atmosphere. This search even connects to the mystery of rogue planets, those starless worlds drifting through the galactic darkness. A gas giant ejected from its solar system could potentially drag its moons along, and tidal heating might provide enough warmth for life to persist in a perpetual, sunless night beneath an icy crust. Could life be huddled around a volcanic vent on a moon, warmed from within by the gravitational embrace of its giant parent? Are these hidden ocean worlds the true cradles of life in the cosmos, outnumbering Earth-like planets by the billions? The quest to find them forces us to look not just at the planets, but at the delicate dance of shadows and gravity that might reveal their silent, orbiting companions. A silent, drifting ocean could exist in the absolute cold and dark between the stars, untethered from any sun. This is the 24th cosmic conundrum, the proliferation of rogue planets. These are worlds that have been flung out of their native solar systems or that formed in lonely isolation, and they may vastly outnumber the stars in our galaxy. They are cosmic ghosts nearly impossible to see directly, their presence betrayed only by the subtlest of tricks. When one of these dark wanderers passes in front of a distant background star, its gravity acts as a lens, bending and magnifying the star's light for a brief, telltale moment. This phenomenon, gravitational microlensing, is our primary window into this invisible population. Surveys like the Optical Gravitational Lensing Experiment, or OGLE, have scanned the crowded star fields toward the galactic center, catching these fleeting brightenings. Theorists like Piazzamek Emroz have analyzed these events, estimating there could be billions, even trillions, of these free-floating worlds adrift in the Milky Way alone. How do planets become orphans? The primary culprit is gravitational chaos within young planetary systems. As giant planets like Jupiter and Saturn jostle for position, their immense gravity can play a game of cosmic pinball, flinging smaller, rocky worlds out into the interstellar void. In some dramatic simulations, an entire system can become unstable, ejecting multiple planets and leaving behind a scarred and simplified family. Some of the smallest rogue planets might not be ejected at all, but instead form like failed stars, collapsing directly from a cloud of gas and dust too small to ignite into a star. These are the planetary mass brown dwarfs, detected by infrared telescopes like WISE as faint, warm embers against the cold backdrop of space. The most profound question is whether these sunless worlds could harbor life. Without a star to provide warmth, their surfaces are frozen wastelands. But deep beneath a thick crust of ice, a rogue planet could maintain a liquid ocean for billions of years, heated by the slow decay of radioactive elements in its core and by the relentless squeeze of tidal forces from a large moon it managed to hold onto during its ejection. In such a subsurface ocean, bathed in perpetual darkness, life could potentially cling to existence around hydrothermal vents, completely independent of photosynthesis. Could the most common abode for life in the universe be these dark, wandering worlds? Their sheer numbers make the idea compelling. This has even led to the speculative idea that some dark matter, the mysterious substance holding galaxies together, could be composed of countless rogue planets. While current observations rule them out as the primary component, their collective mass is still a significant, hidden part of our galactic inventory. These lonely vagabonds are fossils of planetary system evolution, telling a story of violent beginnings and gravitational turmoil. Their silent journey through the galaxy forces us to expand our definition of a habitable world, asking if life requires the light of a star, or if it can flourish in the deep, internal heat of a world without a sun. And as we contemplate the possibility of life in such profound isolation, we are reminded of a single, brilliant signal from the depths of space that seemed to shout, then vanished without a trace. That single, brilliant signal from the depths of space did shout just once and then vanished forever. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear recorded a pulse of such astonishing power and precision that the astronomer Jerry Amon, upon reviewing the data printout, famously circled the alphanumeric sequence and wrote one word in the margin: "Wow." This is the 25th cosmic conundrum, the wow signal, a ghost in the machine that remains the most compelling and most frustrating candidate in the history of the search for extraterrestrial intelligence. The signal was not random static, it was a narrowband transmission focused on the specific frequency of the hydrogen line, 1420 MHz, a frequency many scientists had reasoned would be a natural choice for an advanced civilization trying to signal its existence across the interstellar void. It was loud, 30 times stronger than the background noise, and it lasted for a full 72 seconds, the exact duration the Big Ear telescope could hold a fixed point in the sky. And then it was gone. Jerry Amon himself has said that the signal was so unique, so artificial in its character, that he knew it was something special. Despite repeated and exhaustive searches of that same patch of sky in the constellation Sagittarius, the signal never returned. For decades, the mystery festered. Was it a military transmission, a secret satellite, or a bizarre form of radio interference? Each possibility was systematically investigated and ruled out. More recently, a theory emerged that it could have been caused by hydrogen clouds surrounding a passing comet. But this, too, fell apart under scrutiny, as the specific comets proposed were not in the telescope's field of view at that precise moment. The WOW signal stands as a perfect, solitary data point, a shout in the cosmic dark with no echo. It shares a lineage with other tantalizing false alarms that ultimately led to profound discoveries. The first pulsar signals, detected in 1967 by Jocelyn Bell Burnell, were so regular and artificial seeming that the team jokingly labeled them LGM for little green men. They turned out to be the natural lighthouse beacons of spinning neutron stars, a reminder that the universe is full of natural phenomena that can mimic intelligence. This is the fundamental challenge of SETI, distinguishing a deliberate signal from the endless cosmic noise and human-made interference that clutters the radio spectrum. Modern efforts have evolved far beyond listening for simple pulses. The Allen Telescope Array in California is a dedicated SETI instrument that can observe multiple star systems simultaneously, scanning for more complex technosignatures, the spectral signs of technology. It looks for laser pulses, the waste heat of hypothetical Dyson spheres, or the chemical signatures of industrial pollution in an exoplanet's atmosphere. Meanwhile, projects like SETI at home have harnessed the collective power of millions of personal computers worldwide, allowing volunteers to sift through mountains of radio telescope data in the background, a global citizen science network searching for that one in a billion pattern. The WOW signal forces us to confront the nature of time and our place within it. Was it a targeted beacon that swept past Earth for a fleeting moment, never to point our way again? Was it the catastrophic remains of a one-time astronomical event we cannot yet conceive? Or was it indeed a message, a cosmic hello that arrived, was noted, and faded before we had the chance to reply? How should we prioritize such singular, unrepeatable events in our search? Do we file them away as intriguing curiosities, or do they represent the most likely form of contact we will ever have, a brief, brilliant flash in an otherwise silent universe. This solitary signal is a haunting reminder that the evidence we seek may not be a persistent broadcast, but a momentary spark, leaving us to wonder if we were just a second too late to hear the rest of the conversation. That profound silence, whether from the cosmos or from a single, unrepeatable signal, unfolds within the relentless and irreversible flow of time itself. Our universe possesses a distinct arrow, a one-way street from a past of exquisite order to a future of increasing disorder. This is the 26th cosmic conundrum, the nature and origin of time's arrow. We remember yesterday and anticipate tomorrow, but why is the past fixed and the future open? The clue lies in a concept called entropy, a measure of disorder. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A shattered glass does not spontaneously reassemble, and cream stirred into coffee never unstirs itself. This relentless march toward disorder gives time its apparent direction, but this raises a deeper question. Why was the entropy of the universe so incredibly low in the first place? The Big Bang represents a state of almost unimaginable order, a smooth, dense, and hot soup with exceptionally low entropy. Physicists like Sean Carroll argue that this initial condition is the ultimate source of time's arrow. The universe has been unraveling, becoming more disordered and complex ever since that singular starting point. We can see this cosmic gradient etched into the sky. The cosmic microwave background is a snapshot of a young, smooth, and low-entropy universe. Today, we see a cosmos filled with complex structures like galaxies and stars, which represent pockets of local order, but these come at a great cost. The energy required to build a star or a planet is dissipated as waste heat, increasing the overall entropy of the universe far more than the local order decreases it. A refrigerator creates a cold, ordered space inside, but it does so by expelling even more heat and disorder into your kitchen. The cosmos is the ultimate kitchen, steadily warming up. This directionality is strangely linked to the microscopic world. The fundamental laws of physics, for the most part, are time-symmetric. A film of two electrons repelling each other looks perfectly normal whether played forward or backward. Yet we have observed a tiny crack in this symmetry. Certain particle decays exhibit a phenomenon known as CP violation, where matter and antimatter behave slightly differently. This implies a corresponding violation of time reversal symmetry, suggesting that even at the most fundamental level, time has a preferred direction. This microscopic bias, however, is minuscule compared to the overwhelming drive from cosmology. What does our own perception of time add to this puzzle? Our consciousness seems to flow along with the thermodynamic arrow, our memories forming as our brains, physical systems themselves, record information in a way that increases entropy. This leads to a truly bizarre thought experiment, the Boltzmann brain paradox. In an eternally existing universe, random thermal fluctuations could, by sheer chance, assemble a fully formed, conscious brain out of the chaos. Such a disembodied observer would momentarily pop into existence with a false memory of a past that never was. The fact that we are not such fluctuations, but instead are the products of a long, ordered cosmic evolution, is a powerful argument that our universe has a definite beginning and is not in an eternal, high-entropy state. Could the arrow of time be a local phenomenon? In a vast multiverse, other bubble universes might have different initial conditions. In some, entropy might have started high and decreased, meaning their inhabitants would perceive time as flowing backward from our perspective. They would remember the future and find the past unpredictable. Laboratory tests continue to probe the foundations of time. Experiments with entangled particles and neutral mesons are searching for any further evidence of time reversal violation, any clue that might explain why the past is so different from the future. Is the relentless flow of time an inescapable part of our reality, or is it an emergent property, an illusion born from our unique position in a cosmic story that began with a state of spectacularly low entropy? This inevitable progression from order to disorder forces us to confront the ultimate consequence of this cosmic trajectory, the final fate of everything. That inevitable progression from order to disorder charts a course toward an ultimate, silent finale. The 27th cosmic conundrum confronts the ultimate fate of the universe, a destiny dictated by the subtle properties of dark energy. We are living in a golden age of cosmic structure, but this era of brilliant galaxies and active stars is a fleeting chapter in an epic that spans trillions of years. Project forward, and the cosmos faces several possible ends, each more desolate than the last. The most widely accepted scenario is the Big Freeze or heat death. In this future, the universe continues to expand and accelerate forever. All the usable energy, the free energy that powers stars and life, will eventually be exhausted. The last stars will flicker out, black holes will slowly evaporate via Hawking radiation, and the cosmos will approach a state of absolute equilibrium, a lukewarm sea of diluted particles and radiation where no further work is possible. It is the ultimate triumph of entropy. But what if dark energy is not a constant? A more terrifying possibility is the Big Rip. If dark energy strengthens over time, evolving into something theorists call phantom energy, its repulsive force would eventually overcome all other forces in the universe. First, galaxy clusters would be torn apart, then individual galaxies. As the end nears, stars and planets would be ripped from their gravitational moorings. In the final moments, atoms themselves would be shredded, and finally, the very fabric of spacetime would be torn asunder. The timeline for this apocalypse depends on the dark energy equation of state, a parameter denoted by W. Our most precise measurements from supernova and the cosmic microwave background constrain this value to be very close to -1, consistent with a cosmological constant. But the error bars still allow for the phantom regime, leaving the door open to this violent end. Physicist Lawrence Krauss has eloquently framed this cosmic choice, weighing the cold, eternal silence of heat death against more exotic possibilities like cyclic models, where a new universe might be born from the ashes of our own. This leads to another speculative rebirth, the idea of vacuum decay. Our current vacuum state, the underlying energy of empty space, might not be the true lowest energy state. It could be a false vacuum, a metastable valley in a vast cosmic landscape. If a quantum event triggered a decay, a bubble of true vacuum could form and expand at the speed of light, rewriting the laws of physics as it goes and potentially birthing a new universe with entirely different properties. This is a prediction that emerges from the string theory landscape, where countless vacuum states are possible. The long-term calendar for our universe is staggering. Star formation will peak in a few billion years and then steadily decline as gas is locked away in dead stars and ejected from galaxies. In about 100 trillion years, the last star will be born, and the cosmos will enter a degenerate era, dominated by the cold remnants of stellar evolution. Could any form of life or information processing persist in such a dying universe? Some theorists, like Freeman Dyson, have speculated about civilizations that could harness energy on unimaginably long timescales, slowing their thought processes to match the cooling of the cosmos. Yet, in a heat death scenario, even this becomes impossible as temperatures homogenize and no energy gradients remain. This ultimate destiny is deeply intertwined with the holographic principle. If our reality is a projection from a two-dimensional surface, then the final state of the universe might be a frozen, maximally entangled hologram, a perfect and static record of all the information that ever was. What meaning can we find in a cosmos destined for such profound silence or violent dissolution? The fate of the universe is not just a distant prediction, it is a reflection of the fundamental forces that have woven our existence from the very beginning, and it forces us to ask if our local pocket of order can ever truly comprehend the final, overwhelming victory of disorder. That ultimate frozen hologram is not just a metaphor for the end, but a radical clue to the universe's true nature. The 28th cosmic conundrum is the holographic principle, an idea so profound it suggests our three-dimensional reality is a magnificent illusion. What if the universe we perceive, with its vast galaxies and swirling nebulae, is actually a holographic projection from information stored on a distant, two-dimensional surface? This concept emerges from the fiery heart of black holes. Stephen Hawking showed that a black hole's entropy, its ultimate information content, is not proportional to its volume, but to the surface area of its event horizon. This was the first hint that the information needed to describe a volume of space might be fundamentally limited by the area surrounding it. The principle was solidified by the work of theorists like Leonard Susskind and Gerard T. Hooft, who proposed that the universe itself obeys this rule. The most concrete realization of this idea is the AD-S/CFT correspondence, a mathematical masterpiece discovered by Juan Maldacena. It provides a perfect dictionary, a duality between a universe with gravity, like the space inside a black hole, and a quantum field theory without gravity living on its lower dimensional boundary. It is as if the entire complex three-dimensional world inside a box could be completely described by a set of rules painted on the box's two-dimensional walls. This framework elegantly resolves the black hole information paradox, as the information about everything that falls in is not lost inside the singularity, but is perfectly preserved and encoded on the event horizon. It is then slowly and chaotically radiated back out via Hawking radiation. The implications ripple through all of physics. If gravity and spacetime are not fundamental, but emergent from a quantum system of information, it offers a potential path to unifying general relativity with quantum mechanics. This idea is being tested not with giant telescopes but in tabletop experiments. Physicists use ultra-cold atoms, chilled to near absolute zero and arranged in optical lattices to create quantum simulators. These controlled systems can be designed to mimic the mathematics of a holographic universe, allowing scientists to observe how properties like entanglement entropy, a measure of quantum connection, might give rise to the very geometry of spacetime. The more entangled the quantum bits on the boundary are, the more connected the spacetime in the bulk appears. This suggests that space itself may be woven from the threads of quantum entanglement. Could we one day simulate an entire universe in a laboratory? The holographic principle does not rule it out, raising the dizzying possibility that our own cosmos is a simulation running on a vast computer in a higher dimensional reality. But if reality is fundamentally informational, a cosmic code projected into the three dimensions we experience, where does that leave our own conscious perception of this grand illusion? If reality is a holographic projection, what does that make the observer peering into the illusion? This brings us to the 29th cosmic conundrum, the profound and perplexing role of consciousness in the universe. At the heart of quantum mechanics lies a deeply strange idea, the measurement problem. In the famous double-slit experiment, a single electron fired at a barrier with two slits behaves like a wave, passing through both openings and creating an interference pattern. Yet, the moment we place a detector to observe which slit it goes through, the electron behaves like a single particle. The interference pattern vanishes. The act of observation itself seems to collapse the wave function, forcing a fuzzy cloud of possibilities into a single, definite reality. This suggests that the universe's properties may not be fixed until they are measured, raising the unsettling question of whether consciousness itself is the ultimate architect of reality. Is the moon there when no one is looking? The physicist John Wheeler framed this with his participatory anthropic principle, proposing that we are not just bystanders in the cosmos, but active participants in bringing the universe into being. This connects directly to the anthropic principle in cosmology, which notes that the fundamental constants of nature, from the strength of gravity to the mass of the electron, appear exquisitely fine-tuned for the emergence of life. If any one of these numbers were slightly different, atoms would not be stable, stars would not shine, and life as we know it would be impossible. Is this staggering coincidence mere luck, or evidence that the universe is in some sense meant to be observed? The Nobel laureate Roger Penrose offers a radical synthesis with his theory of orchestrated objective reduction. He proposes that consciousness is not a classical computational process, but a quantum phenomenon. In this view, the cytoskeletal structures within our brain's neurons are the site of quantum computations. The collapse of the wave function is not triggered by conscious observation, but by an objective threshold rooted in the fabric of spacetime itself, a process where quantum gravity influences cognition. This would mean our conscious awareness is intimately woven into the most fundamental laws of physics. But what is consciousness really? Philosopher David Chalmers calls this the hard problem of qualia. We can map the neural correlates of a sensation, like the redness of red, but we cannot explain why the firing of certain neurons is accompanied by a subjective, inner experience. Why is there something it is like to be you? Theories like integrated information theory attempt to tackle this by proposing that consciousness is a fundamental property of any sufficiently complex system that can integrate information. In this view, consciousness is not exclusive to brains, but exists on a spectrum, potentially present in simpler systems or even, on a cosmic scale, in the universe itself. Could the cosmos, with its intricate web of quantum entanglement and information processing, possess a form of self-awareness? Advanced cosmological simulations are now being used to test the limits of these ideas, exploring whether the presence of an observer, even a simulated one, can alter the apparent evolution of a virtual universe. Brain science using fMRI and EEG meticulously charts the neural correlates, identifying which brain networks light up during specific conscious states, yet the ghost of subjective experience remains stubbornly in the machine. This inquiry forces us to the edge of science and philosophy. Is consciousness a rare and accidental emergent property on a tiny planet, or is it a fundamental feature of a self-knowing cosmos? The answer may determine whether we are lonely inhabitants of a blind, mechanical universe or active participants in a reality that is, in some deep and mysterious way, coming to know itself. And this contemplation of being and awareness inevitably leads us to the final, most fundamental question of all, the nature of nothingness itself. That contemplation of being and awareness inevitably leads us to the final frontier of thought, the 30th cosmic conundrum, the nature of nothingness and the origin of something. Why is there a universe at all rather than a featureless, eternal void? This question forces us to confront the vacuum of space, which is not truly empty. According to quantum field theory, the void is a seething sea of activity, where virtual particles and their antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. This quantum foam is a perpetual flicker of something from nothing, a hint that absolute nothingness may be an unstable state. Physicist Lawrence Krauss has explored the idea that the entire universe could be a quantum fluctuation on a grand scale, a fortunate bubble of something that simply grew and persisted. The mathematics of quantum gravity suggests that a universe can spontaneously nucleate from nothing without a cause, because the positive energy of its matter and motion is perfectly balanced by the negative energy of its gravitational field. The total energy of the cosmos could be precisely zero, making its creation from nothing not only possible but perhaps inevitable. This leads to the no-boundary proposal by Stephen Hawking and James Hartle, which describes a universe with no singular beginning in time. In this view, asking what happened before the Big Bang is like asking what is north of the North Pole. Time itself becomes a dimension that smoothly closes off, and the universe arises from a single, self-contained quantum event. The inflationary vacuum that drove the universe's rapid expansion is also a form of something, a peculiar state with a high energy density. Could our universe be just one bubble in a vast cosmic landscape of possibilities, a single universe in an endless multiverse? String theory suggests a staggering number of possible vacuum states, perhaps 10 to the 500 different types, each with its own physical laws and constants. In this eternal inflation scenario, new bubble universes are constantly being born from the decay of a parent vacuum, an endless froth of cosmic creation where most universes are stillborn or devoid of life, and we simply exist in one that works. The dark energy accelerating our expansion could be the energy of our local vacuum, a specific valley in this vast landscape. But what does nothing even mean? Philosophers debate whether a true void, a complete absence of space, time, and physical law, is even a coherent concept. Could multiple universes arise and die in an endless cyclic rhythm, with each Big Bang emerging from the collapse of a previous cosmos? Observations of the cosmic microwave background may hold clues. Certain large-scale anomalies in its temperature map, features that seem unlikely within our standard model, could be fossil imprints from a universe that existed before our own, scars from a previous cosmic cycle. Quantum cosmology calculations trace the wave function of the universe back to its origin, suggesting that the most probable state is a tiny, smooth quantum nugget. Is the concept of nothing a useful starting point, or is it a human invention that physics has rendered obsolete? This ultimate mystery, the leap from pure potential to tangible reality, is the final thread in our cosmic journey, a question that echoes back through every conundrum we have explored, from dark matter to the nature of consciousness. It asks not just how the universe works, but why it dares to exist in the first place. These 30 threads of cosmic mystery are not separate puzzles, but a single, shimmering web. The ghostly pull of dark matter sculpts the galaxies whose spin first betrayed its presence, while the repulsive force of dark energy dictates their ultimate fate, stretching the cosmic tapestry into which they are woven. At the heart of a black hole, the conflict between quantum law and gravitational force forces us to invent ideas like the holographic principle, suggesting that space-time itself may be a projection from a more fundamental reality, a reality where information is the true currency of existence. This grand synthesis reveals a universe where the largest structures and the smallest particles are inextricably linked, where the initial conditions that allowed matter to dominate are echoed in the lithium deficit of ancient stars. Leading cosmologists and particle physicists now speak with one voice, emphasizing that a breakthrough in one domain, like detecting a dark matter particle, would send shockwaves through all the others, potentially explaining the This collaborative spirit is the engine of modern discovery, embodied by international endeavors like the Event Horizon Telescope, a global array that gave us our first glimpse of a black hole's shadow. Technological leaps are accelerating this convergence at a breathtaking pace. The James Webb Space Telescope peers back to the dawn of the first galaxies, testing our theories of structure formation, while here on Earth, quantum computers simulate the conditions of the early universe, offering a new lens on inflationary physics. This is not a solitary pursuit. Public engagement through citizen science projects like Galaxy Zoo, where volunteers classify millions of galaxies, proves that the desire to map the cosmos is a deeply human impulse. With this collective effort comes profound responsibility. The same search that maps the cosmic web might one day stumble upon a technosignature, forcing us to confront earth-shaking ethical questions. How would such a discovery reshape our understanding of our own place in existence, and what would be our duty in reply? The inspiration drawn from these mysteries already fuels innovation on our own world, from the global positioning system that relies on general relativity to new medical imaging technologies born from particle detectors. As we stand at this crossroads of knowledge, we must ask how these conundrums will transform with the next flood of data from new observatories. What new mysteries will we uncover that we cannot even conceive of today? This grand synthesis is more than a summary of unsolved problems. It is a map of our growing understanding, a testament to a universe that is not only stranger than we imagine, but stranger than we can imagine. Our journey through these 30 cosmic conundrums reveals a universe far grander and more intricate than we could have dreamed, a reality where the ghostly scaffolding of dark matter supports brilliant galaxies, and the empty vacuum of space hums with dark energy. We have moved from the infinitesimal, where quantum threads weave the fabric of spacetime, to the vast, accelerating horizon of the entire cosmos. Each mystery, from the black hole information paradox to the haunting silence of the Fermi-paradox, underscores a beautiful and humbling truth. Our understanding is perpetually unfinished, and our knowledge is a tiny island in a sea of the unknown. The true takeaway is not a list of answers, but a celebration of the process itself, the relentless interplay between bold theoretical leaps and painstaking observation that drives science ever forward. This pursuit expands the horizons of human understanding and fosters a profound, shared sense of wonder, connecting us all under the same cosmic sky. Carl Sagan's timeless words resonate here more than ever. The cosmos is within us. We are made of star stuff. Every atom in our bodies was forged in the heart of a long-dead star, making us not just observers of these enigmas, but active participants in the cosmic story. Which of these puzzles ignites your own curiosity the most, and how will it change the way you look at the night sky? Let this exploration be an invitation, not an end. Keep questioning, keep looking up, and carry this wonder with you. If these mysteries captivated you, subscribe for more deep dives into the universe's greatest secrets. Share this video to spark a conversation, and let us know in the comments which cosmic conundrum captivated you the very most. The greatest discoveries are still waiting, just beyond the light of